And welcome back, AP Calc students. Time for another free response question. This is from the year 2019, and this is question number 4. Number 4 means this is a non-calculator question, and this is also a blend of differential equations and related rates. And so the trend is mixing types here within one question. In earlier years, they were more distinctly one style, but the blend has definitely been a trend here. So this question is similar to earlier in the year when you do related rate questions, and I just want to give you an example. If you remember the questions where you had a conical tank, and it would be the conical tank was leaking or getting filled up, and these were the trickier ones where you had to do a substitution. But if you remember, we had a 5-step method, and we would say the volume here was equal to 1/3 pi r squared h. And if you recall, we would have to do a substitution here because there was a warning that if you had 3 variables, you wanted to look for a substitution. So usually we would use similar triangles, and they might say they'd give us a ratio of the height to the radius, and we would sub out one of these and get this down to a 2-variable equation. And once we did that, we would then take d dt of this, if you recall, and we would find dv dt. Sometimes that was given, sometimes that's what we were solving for. And then we would take d dt of this. Now, if I took the derivative with respect to time to this one's pretty messy, because this is actually, we would have a product rule. And so if I did that one, make sure we can clearly see that's an r. I'm going to go ahead and do that one just to clarify something. Now, the 1/3 pi is a constant here, so if I was to take the derivative of the first, so that would be this part right here, and I'll let h be the second, I would have 2/3 pi r, but since my variables didn't match, I would have dr dt times h. That would be the derivative of the first times the second, and then I would have plus the first, and I would do 1/3 pi r squared times the derivative of the second. Well, the derivative of h would just be 1, but my variables don't match, so I would have to multiply this by dh dt. Okay, so again, this would be the first, and here would be the derivative of the second thing. Okay, and this is the rule kind of was something like, if you have a ton of information, you can have 3 variables, but typically we like to get it down to 2 variables. Okay, just a light review, and then we'd have the information. We would do our box, where, if you recall, we would have all the variables, and we would have the volume, the radius, and the height, and we would have then the rate that each one of them was changing, and we would do that kind of question. Well, that's just a quick refresher. The shape we have right here on this one is much easier. And the thing I want to show you here is that a lot of students get confused. Why is this so much easier? And the reason, whenever you have a cylinder, the reason it's easier is that the radius isn't changing. Clearly you can see the radius is very large on the conical tank, and the radius is getting shorter, so it is a variable. But when you have a conical tank, the radius never changes, therefore it is a constant. So that's an important distinction you want to make right away, because a lot of students say, how come I'm not taking dr dt, etc., going through here? You just get to treat it like a constant. And so our formula here for the volume of a cylinder is going to be pi r squared h, and r is a constant. In fact, in this case, in this example, it would be 1. So you want to keep that in mind. We have the 1/3 for here for the cone, plus both of these vary. In this one, it's just a straightforward equation, plus r is not a variable. The only variable is h. Now, because of that, when I take d dt of this, and this is going to happen here fairly early in the question here, but I just want to review this concept. When I take d dt of this, the derivative of volume is, or v is 1, variables don't match, I have dv dt. And now again, if this is a constant right here, pi r squared is a constant, the derivative of this is just pi r squared dh dt. Now that confuses a lot of students. Now the reason is pi r squared is a constant. So for example, to give you a counterexample, what if I would have said v was equal to 5h? and I wanted to take d dt of that, I would just have dv dt is equal to, the coefficient is just 5 dh dt. So this being a constant, it just treated as any other coefficient. It's just there as I took the derivative of h. Same idea. So that's going to be an important distinction to make. I just wanted to review, because we're kind of locked in usually to having to treat r like a variable, but when it doesn't change, it's not. So they're actually much easier. Okay, so a little review of that concept of a related rate. And so now let's go ahead and look at the question. Question says a cylindrical barrel, and here it is right here. A cylindrical barrel with a diameter of 2 contains collected rainwater, as shown in the figure. The water drains out a valve not shown at the bottom of the barrel. The rate of change of the height of the water in the barrel with respect to time is modeled by dh dt is equal to negative 1/10 rad h, where h is measured in feet and t is in seconds. The volume of a cylinder, they actually provide it for you, pi r squared h. All right, find the rate of change of the volume of the water in the barrel with respect to time when the height of the water is 4 feet. Indicate units of measure. Okay, so with the little review we did here, let's go over here and see what we can do. So first, let's start again. We have a shape here. We have the volume of a cylinder, which is pi r squared h. Okay, and again, we just did that over here. So I'm going to take d dt of this. And so when I take d dt, I get dv dt is equal to pi r squared dh dt. Okay? Now the question says, this says find the rate of change of the volume. So what they're asking us to find is actually dv dt. That's what we don't know. And so even if I go to this, if you were really locked into the old way we did this, you could say, well, I've got the volume, and I've got dv dt, and I've got r, and I've got dr dt, and I have h, and I have dh dt. Now this is not necessary to do, but for those of you that are thinking back to the old way of doing this, you could say, well, the question's asking me to find dv dt. The radius, according to the problem, is equal to 1. The rate it changes, it doesn't, it's 0. The height, and the problem here, I'll find this when the height of the water is 4 feet, so that equals 4. And dh dt, well, if you'll notice, they gave us an equation for dh dt. It's right there. And so dh dt, for when the height is 4, I'm actually going to put in in what they have right here. But they have it's negative 1/10 rad h. And again, this isn't totally necessary to do here, but when the height is 4, I'm just going to write this, dh dt, height of 4, rad 4 is 2. 2 times negative 1/10, that would be negative 2/10, which is negative 1/5. So you want to make sure that you say at the height is equal to 4 dh dt. I'm going to go ahead and write that there. At a height of equal to 4 dh dt, according to the formula here, again, is equal to negative 1/5. And that would be our units here per time. So I think we're in feet per... Are we seconds? Yes, feet per seconds. Okay, so I can even put that there. Feet per second. Okay, so now when I go over to here, the reason I wanted to do that is some of you guys are used to this. This was our equation, step 1. Step 2, take the derivative of it. Here's our box. We filled it in, and now it's time to put it in here. So dv dt is equal to pi. The radius is 1 squared, and dh dt we figured out was negative 1/5. So dv dt for this question is simply negative pi over 5, and it's the volume, and this was in feet, so it's going to be feet cubed per second. Okay, fairly straightforward problem if we've reviewed our whole approach here with related rates. Okay, so that is the first part of the question. A fairly simple equation, and just a related rate one, and we had everything we needed. Okay, now it's time for part B. So I'm going to erase some of my work over here to give me some space to work. So hopefully, if you need those notes, you can just rewind. Okay, and let's see, we'll make a little edge here, and yeah, let's put B here. Okay, so B says when the height of the water is 3 feet, the rate of change of the height of the water with respect to time, is it increasing or decreasing? Explain your reasoning. Now, I like this little question because it's got a little bit of a curveball in there, and it's easy to make a mistake. It says, whenever they want to know, I don't care what it is, and this is why it's good. If you ever get asked something and you want to actually go to the end here and then work backwards, they want to know, is something increasing or decreasing? Well, if you want to know if something's increasing or decreasing, you better take the derivative of it. So what am I taking the derivative of? The rate of change of the height of the water. Is that thing increasing or decreasing? Well, we have to take the derivative of it. I don't care what you're talking about. If you want to know if something's increasing or decreasing, take the derivative of it. This is why this one was a little bit tricky. They're asking, is the rate of change of the height increasing or decreasing? Well, we're going to take the derivative of it. Well, what's a little bit goofy about this one is they gave us dH dt here is equal to negative 1/10 rad h. So the question is this thing increasing or decreasing? Well, if you want to know if this thing's increasing or decreasing, we have to take the derivative of this thing. So what we're going to have to do is take d dt of this. And we'll go ahead and do this, negative 1/10 rad h. Okay, so the derivative of this, now we use our notation of d squared h over dt squared, is equal to, now we're just going to take the derivative of this. Okay, so I'm going to change this to h to the 1/2 because we're going to use our power rule here. Okay, so I have 1/2 times negative 1/10, so that's going to be negative 1/20 h to the negative 1/2, okay, times the derivative, or times dH dt, because my variables didn't match, so I got to go times dH dt. Okay, very easy to miss that little last step there, but I'm taking it with respect to time. So then as we clean this up over here, we'll say, okay, well, d squared h over dt squared is equal to squared. So I'm going to replace dH dt with what it equals. And so I get negative 1/20. And I'm going to go ahead and move h down to the denominator. And I'm going to make that 1 over rad h. You'll see why here in just a second. And then I'm going to replace dH dt with what it equals from earlier here. And so I get negative 1/10. And then it's rad h. Okay. Now, if you'd have wanted, you could have put h equal 3 in there. It's not going to matter, but you're going to see very quickly here what happens. Our rad h in the numerator cancels with the rad h in the denominator. Negative times a negative. This is a little bit peculiar. Honestly, not a huge fan that they did this, but the second derivative is equal to 1/200. Which is fine, but remember, if we want to check increasing or decreasing, your instinct should tell you, okay, there's my second derivative. When is that undefined? When does it equal 0? Well, it's never undefined, and it never equals 0. We don't have anything here. And so if you went to test this like your critical numbers, you still have to test it. We have no points. So no matter what you pick, the second derivative here is going to be a positive number. And since it's positive, it tells me this is increasing the entire time. Now, some of you would have just stopped right here and said, oh, the second derivative is a constant that's positive. Oh, it's always greater than 0. It equals 1/200. That's always greater than 0, which is positive. Therefore, you would conclude it's increasing. So you could do it there, or you could conclude to here. But the main point is your second derivative here is always positive. Therefore, it's increasing. So I'm going to put that right here. I'm going to say d squared h over dt squared is greater than 0 for all, let's see if we had our intervals, for all values. For all values of t. Therefore, dH dt is increasing at a height of 3. Because the question says when the height is 3, is the rate increasing or decreasing? So that's why I'm saying at the time. Probably saying for all values covers it, but there's my conclusion right here. Okay, so just go back to the beginning here. You're asked about something increasing or decreasing. You want to think, okay, I have to take my derivative. turned out as I took my derivative that I was hoping to get some critical numbers, it turned out my derivative was a constant. So I didn't have any numbers to check, but I still had to test the interval. It's always positive, therefore it's always increasing. And there's your answer. Now, the other part of this that you wanted to, you could have just thought about this logically. You could have said, at 3 feet, is the rate of change of the water, of the height of the water with respect to time increasing or decreasing? So remember, they said this thing is filling up with rainwater, but it's also leaking out the bottom. And if you could have said, here's the change in height, it's negative, and you might have looked at that and thought intuitively, at what time is this leaking out of the bottom versus it being filled up? What time is that changing? You could have thought through it that way. But that is our conclusion here for B. All right, and now I guess we'll put C right here. All right, C says, at time t equals 0 seconds, the height of the water is 5. Use separation of variables to find an expression for h in terms of t. Well, this is really just solve the differential equation. So this one's going to be a little bit weird because I'm going to have to work horizontally. So I'm going to do a lot of work vertically and then the next column and the next column. So I'm going to start right here and I'm going to say dh dt is equal to negative 1/10 rad h. So this is just solve a differential equation, and it's a fairly friendly one too. So first step, we're going to separate our variables. So I'm going to do dh divided by rad h is equal to negative 1/10 dt. Okay, then we're going to integrate both sides, and I'm going to integrate here. I'm going to make this h to the negative 1/2 dh, and that is equal to the integral of negative 1/10 dt. Okay, so I separated my variables, integrate both sides, and like I said, I'm going to have to do several little columns here. So let's integrate this side. Add 1 to your exponent, divide by your new exponent. So this becomes h to the 1/2 divided by 1/2. So it's going to be 2 rad h. Okay, 2 rad h from there, and that is going to equal negative 1/10 t plus c. So those are the results of the two integrals. No natural logarithms, no exponentials. This is a fairly friendly differential equation. Okay, so now we're going to solve for c. So I'm going to solve for c. I'm just actually going to write that. Solve for c. And we're going to put in the point where they say in the question, at time t equals 0, the height of the water is 5. So 0, 5 is a point they give us. So now I'm going to say, all right, 2 times rad 5 is equal to negative 1/10 times 0 plus c. Those drop out, and I get c is equal to 2 rad 5. And now I'm going to take that and put it back in. So now I'm here. 2 rad h is equal to negative 1/10 t plus 2 rad 5. Okay? Now I'm going to divide both sides by 2. Jump up to here, divide both sides by 2, and I get rad h is equal to negative 1/20th, dividing by 2 here, or multiplying both sides by half, plus just rad 5. So when I divide by 2, cancels the 2 here and makes that negative 1/20th. Now I'm just going to square both sides, and I get h is equal to negative 1/20th plus rad 5, the quantity squared. Okay, and now if I want to be, I can make it function notation. I'm going to say h, which is a function of time, is equal to negative 1/20th I left off my t, didn't I? Negative 1/20th t plus rad 5, and that is squared. And there is the solution to the given differential equation. So, as I said at the beginning, this is an interesting combo of related rates and differential equations. And even this little wrinkle here about increasing, decreasing. Really, you got to be careful when you check that. Whenever they ask you, is a rate increasing or decreasing? Well, you have to take the derivative of the rate. It's easy to skip that because you already have a rate. That's the curveball for part B. So, a little related rate for part A. Derivative of a rate for part B, and then part C, solving a differential. Okay, so there it is, 2019 question number 4. Thanks for watching. We will see you next time.